March 12, 1982, 0940 hours, Santa Clara, California. Dr. Viktor Mikhailovich Ryzhkov stood in the anteroom of Intel's fabrication facility, dressed in the white cleanroom suit that made him look like an astronaut preparing for a spacewalk, and felt his hands trembling. He was Deputy Director of Research Institute Pulsar in Zelenograd, the Soviet Union's answer to Silicon Valley, a closed city 30 kilometers northwest of Moscow, where the best minds in Soviet microelectronics worked to keep pace with Western semiconductor technology. He had spent 17 years designing integrated circuits, managing production facilities, solving the impossible problems that Soviet engineers confronted daily when trying to manufacture chips with equipment that was obsolete, materials that were impure, and quality control procedures that were inadequate by any reasonable standard. And now, he was about to see how the Americans did it, how they manufactured microprocessors with hundreds of thousands of transistors on a single chip, how they achieved production yields that Soviet facilities could not approach, even with much simpler designs, how they maintained the impossibly clean environments required for modern semiconductor fabrication. He had read the intelligence reports, studied the technical specifications acquired through various means both legal and illegal, examined the stolen chips that Soviet engineers reverse-engineered in desperate attempts to understand Western manufacturing processes. But reading about something and seeing it with your own eyes were fundamentally different experiences. The visit had been arranged through official channels as part of a technology exchange program between the United States and Soviet Union. It was 1982, and détente had given way to renewed tensions, but certain scientific exchanges continued because both sides found them useful. The Americans wanted to demonstrate their technological superiority, to show Soviet engineers how far behind they had fallen, perhaps to intimidate them or to encourage defections. The Soviets wanted intelligence, any scrap of information that might help them close the yawning gap that separated their semiconductor industry from Western capabilities. Ryzhkov was part of a delegation of 7 Soviet microelectronics specialists, officially invited to tour American semiconductor facilities and attend technical conferences. The delegation included engineers from Zelenograd's major research institutes, a representative from the Ministry of Electronics Industry, and at least 2 KGB officers whose technical credentials were thin, but whose interest in Western technology was intense. Everyone understood the real purpose of the visit: gather intelligence, document everything, try to understand how the Americans achieved what seemed impossible to Soviet industry. Their guide was a cheerful Intel engineer named Robert Chen, who seemed genuinely proud of the facility he was about to show them. Gentlemen, welcome to Fab 5. This is one of Intel's most advanced fabrication facilities, where we manufacture the 8086 and 8088 microprocessors, among other products. What you're about to see represents the state-of-the-art in semiconductor manufacturing. Before we enter the cleanroom, I need to explain some basic safety procedures and contamination control measures. The contamination control procedures were extensive. They had already passed through an air shower that blasted loose particles from their cleanroom suits. Now Chen explained that they would enter through a series of airlocks that maintained positive pressure differentials, ensuring that air always flowed from cleaner areas to less clean areas, preventing outside contamination from entering the fabrication environment. The cleanroom itself was classified as Class 100, meaning that each cubic foot of air contained no more than 100 particles larger than 0.5 micrometers. For comparison, normal room air contained millions of particles per cubic foot. Ryzhkov glanced at his colleague, Dr. Anatoly Simonov, chief engineer at Research Institute Electronica, and saw his own thoughts reflected in Simonov's expression: Class 100 cleanroom. Soviet facilities struggled to achieve Class 10,000, and even then the standards were inconsistently maintained. Many Soviet chip fabrication lines operated in environments that would qualify as Class 100,000 or worse by Western standards. Contamination was the single largest cause of defects in Soviet semiconductor production, reducing yields to levels that made manufacturing economically catastrophic. The airlock doors opened, and they entered the fabrication floor. Ryzhkov stopped walking, overwhelmed by what he saw. The clean room stretched before him like something from a science fiction film. A vast space filled with equipment that looked impossibly advanced, impossibly clean, impossibly organized. Automated wafer handling systems moved silicon wafers between processing stations with robotic precision. Photolithography steppers, each one costing millions of dollars, exposed circuit patterns onto wafer surfaces with accuracy measured in micrometers. Chemical vapor deposition chambers grew ultra-thin films of semiconductor materials with atomic layer precision. Ion implanters shot carefully controlled doses of impurity atoms into silicon substrates to modify their electrical properties. Everything was automated, monitored, controlled with a precision that seemed almost obsessive. Display panels showed real-time data on process parameters: temperature, pressure, gas flow rates, deposition rates, exposure times. Computers tracked every wafer through hundreds of processing steps, maintaining complete records of every operation performed on every chip. The entire facility hummed with quiet efficiency, like a perfectly tuned orchestra performing a complex symphony. Our production process involves approximately 300 individual steps, Chen explained, his voice slightly muffled by his cleanroom mask. Each wafer goes through multiple cycles of photolithography, etching, deposition, and doping to build up the complex three-dimensional structures of the integrated circuits. The entire process takes about 6 weeks from start to finish for our current products. 300 steps, 6 weeks. Ryzhkov knew that Soviet facilities required 3 to 4 months to produce chips with far fewer transistors and much simpler architectures. The Americans were moving twice as fast, producing chips 10 times more complex, with yields that were 3 to 5 times higher. Every metric demonstrated overwhelming American superiority in semiconductor manufacturing. They moved to a photolithography station where Chen explained the process in detail. This is a GCA wafer stepper, one of the most advanced lithography tools in the world. It uses ultraviolet light to expose circuit patterns onto the wafer surface. The optical system has a resolution of about 1.5 micrometers, which allows us to create circuit features smaller than anything visible under a normal optical microscope. We can place millions of transistors on a chip the size of your fingernail. 1.5 micrometers. Ryzhkov's stomach tightened. Soviet photolithography equipment had resolution limits of about 3 to 4 micrometers at best, using optical systems that were crude by comparison. This meant American chips could pack 4 times as many transistors into the same area, achieving performance and complexity that Soviet designers could not approach. And it was not just the equipment that was superior. It was the entire ecosystem of supporting technologies, materials, processes, and expertise. "What is your production yield for the 8086 processor?" asked Colonel Grigory Volkov, one of the KGB officers masquerading as an electrical engineer. Chen smiled. "Our current yields for the 8086 are approximately 70% for fully functional chips at rated speeds. We also bin some chips that don't quite meet full specifications and sell them as lower speed versions. When you account for that, our effective yield is closer to 85%. The number hit Ryzhkov like a physical blow. 70% yield for a chip with 29,000 transistors. Soviet facilities were achieving yields of 20–30% for chips with fewer than 10,000 transistors. The disparity was so large that it seemed impossible that both industries were supposedly building similar products using similar physical principles. It was as if Soviet and American engineers existed in different technological universes governed by different physical laws. They spent 4 hours touring the facility, and with each passing hour, Ryzhkov's professional confidence eroded like sand before a tide. The scale was impressive, but scale alone was not what disturbed him. The Soviet Union could build large facilities if necessary. What disturbed him was the systematic excellence, the relentless attention to detail, the obsessive pursuit of perfection in every aspect of the manufacturing process. Intel's quality control was comprehensive and unforgiving. Every batch of chemicals was tested for impurities. Every piece of equipment was calibrated regularly. Every wafer was inspected at multiple points in the process using automated optical inspection systems that could detect defects smaller than a human hair. Any anomaly triggered investigations to determine the root cause and prevent recurrence. The entire system was designed to identify and eliminate sources of contamination, variation, and error. Soviet facilities operated on different principles. Equipment broke down frequently and was repaired with whatever parts were available, regardless of whether those parts met original specifications. Chemicals arrived with impurity levels that varied wildly between batches because Soviet chemical manufacturers operated with poor quality control. Wafers were inspected manually by technicians whose training was inconsistent and whose incentive was to pass marginal products rather than reject them and fail to meet production quotas. The entire system lurched from crisis to crisis, with each emergency requiring intervention from ministry officials who knew nothing about semiconductor physics but had the authority to override technical decisions. At 14:30 hours, Chen led them to a conference room overlooking the fabrication floor. Through the glass walls, they could see the clean room stretching into the distance. Hundreds of millions of dollars worth of equipment working in perfect coordination to manufacture chips that represented the cutting edge of human technological achievement. Coffee and sandwiches were served, an attempt at hospitality that felt surreal given what they had just witnessed. "Gentlemen, I hope you found the tour informative," Chen said. "Intel is committed to advancing semiconductor technology, and we believe international cooperation can benefit everyone. Do you have questions about what you've seen?" The delegation sat in silence for a moment. Ryzhkov glanced at his colleagues and saw the same expression on every face, a mixture of awe, despair, and barely concealed humiliation. These were among the most talented engineers in the Soviet Union, men who had dedicated their careers to advancing Soviet microelectronics, and they had just been shown with absolute clarity that their entire industry was hopelessly backward by Western standards. Finally, Simonov spoke, his voice carefully neutral. "Mr. Chen, your manufacturing processes are very impressive. Tell me, how do you maintain such stringent contamination control standards? What are your procedures for training cleanroom personnel?" Chen launched into a detailed explanation of Intel's contamination control protocols, the air filtration systems, the constant monitoring of particle counts, the rigorous training programs for cleanroom workers. But Ryzhkov was only half listening. He was thinking about what he had seen, trying to understand how Soviet microelectronics had fallen so far behind, trying to determine whether the gap could ever be closed. The problem was systemic and multifaceted. Soviet semiconductor manufacturers lacked access to the specialized equipment that Western companies could purchase from a global network of suppliers. Companies like GCA, Perkin-Elmer, and Applied Materials sold advanced lithography tools, etching systems, and deposition equipment to Western chipmakers. These companies invested heavily in research and development, constantly improving their products in response to customer demands for better performance. Soviet manufacturers had to build all their own equipment using domestic designs and components, and they built it poorly because Soviet machine tool industry was itself backward. The materials problem was equally severe. Modern semiconductor manufacturing required ultra-pure silicon with impurity levels measured in parts per billion. It required exotic gases and chemicals with precisely controlled compositions. It required photoresist materials with resolution capabilities matched to the wavelength of light used in lithography systems. Western chemical companies supplied these materials to semiconductor manufacturers, competing with each other to provide better purity and more consistent quality. Soviet chemical industry could not match these capabilities, forcing chip manufacturers to work with inferior materials that limited performance and reduced yields. But perhaps the most fundamental problem was cultural and economic. Intel was a private company competing in a global marketplace where success required continuous innovation and quality improvement. If Intel's products failed to meet customer requirements, customers would buy from competitors like Motorola, Zilog, or Advanced Micro Devices. This competitive pressure drove relentless improvement in every aspect of the business, from design to manufacturing to testing. Companies that could not keep pace went bankrupt or were acquired by stronger competitors. Soviet microelectronics companies faced no such pressure. They received funding from the state regardless of whether their products met performance specifications or delivery schedules. They had guaranteed customers in Soviet military programs and civilian applications that had no alternative suppliers. Innovation happened slowly, if at all, driven by individual engineers' dedication rather than systematic pressure to improve. And when programs failed, as many did, the consequences fell on engineers and technicians who were blamed for not meeting impossible targets set by planners who understood nothing about semiconductor physics. The tour concluded at 1600 hours and the delegation was transported to their hotel in San Francisco. That evening, they gathered in Volkov's suite for the debriefing that everyone knew was coming. The KGB colonel sat at the head of the table, his expression carefully controlled, giving nothing away. But Ryzhkov could read the tension in his posture. Volkov had seen exactly what they all saw, and he was trying to determine how to report it without appearing defeatist. "Comrades, we must compile a comprehensive report on what we observed today," Volkov began. "Moscow will expect detailed technical specifications, manufacturing methods, organizational structures. But we must also provide context and analysis. What are your initial assessments?" Silence. Nobody wanted to speak first, to be the one who stated the obvious conclusion that every person in the room had already reached. Finally, Ryzhkov decided that professional honesty was more important than political caution. "Comrade Colonel, I believe we are not competing in the same league as the Americans in semiconductor manufacturing. What we saw today demonstrates an industrial capability that is perhaps 10 to 15 years ahead of Soviet production. The equipment quality, the contamination control, the automation, the materials purity, these are not areas where we can achieve parity through incremental improvements. We would need fundamental restructuring of our entire microelectronics industry to approach what Intel has accomplished." Volkov's eyes narrowed. "That is a very serious assessment, Comrade Ryzhkov. Are you suggesting that Soviet microelectronics industry is inferior to capitalist production?" Ryzhkov met his gaze steadily. "I am stating an observable fact, Comrade Colonel. Intel produces chips of greater complexity at higher volumes with better quality control than we achieve. I saw their production line. I spoke with their engineers. Unless you believe everything we were shown was an elaborate deception, which I do not, then we must acknowledge that they have significant advantages in technology and organization." Simonov spoke up, his voice thoughtful rather than defensive. "I reached similar conclusions. The Americans have invested enormous capital in advanced equipment and quality control. Their manufacturing engineers use tools and processes that we simply do not possess. And their materials quality suggests supply chains far more sophisticated than what we have access to in the Soviet economy. But surely they showed us only what they wanted us to see," protested Dr. Igor Karpov, an engineer from the Ministry of Electronics Industry. "This could be their most advanced facility, not representative of American industry as a whole." "I considered that possibility," Ryzhkov replied, "but Chen mentioned that Intel operates multiple facilities with similar capabilities, that other American manufacturers like Motorola and Texas Instruments have comparable equipment and processes. If this is simply one exceptional facility, why would they tell us about all the others? No, comrades, I believe what we saw is representative of standard American practice, at least in their advanced semiconductor sector." The discussion continued for another 3 hours, each engineer contributing observations, raising questions, trying to find some explanation that did not require admitting comprehensive Soviet inferiority. But every analysis led to the same conclusion. The Americans had built a semiconductor industry that operated on fundamentally different principles from Soviet production, and those principles generated results that central planning could not match. Over the following 2 weeks, the delegation visited other facilities. At Advanced Micro Devices in Sunnyvale, they observed production of microprocessors that AMD had reverse engineered from Intel's designs, demonstrating that even Western companies engaged in what the Soviets called creative borrowing, but did it more successfully because they had the manufacturing capabilities to produce working copies. At Fairchild Semiconductor in San Jose, they toured research laboratories developing new process technologies that would enable even smaller transistors and more complex chips. At Applied Materials in Santa Clara, they saw the equipment that American chip makers used, understanding for the first time that the semiconductor industry was supported by an entire ecosystem of specialized suppliers that did not exist in the Soviet economy. Each visit reinforced the same fundamental reality. The technology gap was real, it was substantial, and it was growing. For every advance Soviet engineers made through reverse engineering or indigenous development, American companies made 3 or 4 advances that pushed the frontier even further ahead. Soviet microelectronics was trapped in a perpetual catching-up mode, always copying designs that were already obsolete by Western standards, never quite achieving the manufacturing quality needed to make those copies work reliably. On March 28, 1982, the delegation returned to Moscow. Ryzhkov spent the flight writing his report, trying to find language that conveyed the truth without sounding disloyal or defeatist. It was a delicate balance. He needed to inform Soviet leadership about what he had observed, but he also knew that unwelcome truths were often punished regardless of their accuracy. His final report ran to 89 pages, dense with technical details, manufacturing statistics, equipment specifications, and strategic assessment. The conclusion was carefully worded but unambiguous. The United States possessed overwhelming advantages in semiconductor manufacturing capability, equipment quality, materials purity, and process control. Soviet production could not match American performance using current methods and available resources. Closing the gap would require massive investment in equipment development, establishment of high-purity materials supply chains, complete renovation of fabrication facilities to achieve proper contamination control, and probably some adoption of market mechanisms to drive innovation and quality improvement. The report was classified top secret and distributed to senior officials in the Ministry of Electronics Industry, the State Committee for Science and Technology, and the Central Committee of the Communist Party. Ryzhkov never learned what response it generated, if any. He was not reprimanded or punished, but he was not promoted either. His career continued on the same trajectory, managing research programs at Pulsar, while watching Soviet microelectronics fall steadily further behind Western capabilities. But the report did not disappear entirely. Years later, after the Soviet Union collapsed and archives were open to researchers, historians discovered Ryzhkov's assessment among thousands of similar intelligence reports. They found that Soviet leaders had known about the technology gap, had received accurate information from engineers and technical specialists, had understood the structural problems with their industrial system, and they had done essentially nothing in response. Why? Because fixing the problems would require admitting that the fundamental premises of the Soviet system were wrong. Market competition worked better than central planning for driving innovation in complex, high-technology industries. Private companies made better decisions about technology investments than state planners who answered to party ideology rather than engineering reality. Quality improvement required economic incentives that Soviet managers and workers lacked. These were truths that Soviet leadership could not acknowledge without undermining the entire basis of their political authority. So the reports were filed, classified, and effectively ignored. Soviet microelectronics continued producing chips using methods that fell steadily further behind Western competitors. The technology gap that Ryzhkov had documented in 1982 only grew wider over the following decade. Western companies moved from 1.5 micrometer manufacturing processes to 1.0 micrometer, then to 0.8 micrometers, then to zero point 0.5 micrometers and beyond, each generation packing more transistors onto chips, improving performance, reducing power consumption, lowering costs. Soviet facilities struggled to achieve the 1.5 micrometer process capabilities that Intel had demonstrated during Ryzhkov's visit, and by the time they succeeded, Western industry was already 2 generations ahead. The copying strategy that Soviet microelectronics relied on became increasingly problematic. In the 1970s, Soviet engineers had successfully reverse-engineered chips like the Intel 8080 microprocessor, producing clones like the KR580VM8ZUA that were functionally compatible with Western designs. These chips were obsolete by Western standards by the time Soviet versions reached production, but they were good enough for many Soviet applications, and reverse engineering was faster and cheaper than independent development. But as chips became more complex, reverse engineering became exponentially more difficult. The Intel 8080 had about 4,500 transistors. The 8086 that Ryzhkov had seen in production at Intel had 29,000 transistors. By the mid-1980s, Western microprocessors contained hundreds of thousands of transistors, and by the early 1990s, millions. Reverse engineering these complex designs required understanding not just the logical architecture, but also the manufacturing processes, the materials science, the test methodologies, all of which were closely guarded trade secrets that Western companies protected aggressively. Soviet engineers tried desperately to keep pace. They acquired Western chips through various means, both legal and illegal, slicing them into thin sections to photograph the internal structures layer by layer, painstakingly reconstructing the circuit designs from these images, attempting to replicate the manufacturing processes. It was tedious work requiring enormous technical skill, and even when Soviet engineers succeeded in understanding a design, they often lacked the manufacturing capabilities to produce working copies. The most notorious example of Soviet technology acquisition was revealed in 1981 when a French intelligence officer named Vladimir Vetrov, codenamed Farewell, provided the CIA with documents detailing Soviet efforts to steal Western technology. The Farewell dossier, as it became known, included a shopping list of thousands of Western technologies that the Soviet Union was attempting to acquire through espionage. Semiconductor manufacturing equipment, computer designs, software, telecommunication systems, the list was comprehensive and damning. It revealed that the Soviet technological establishment was overwhelmingly dependent on stolen Western technology, that indigenous innovation had essentially ceased in many sectors, and that even with massive technology theft, Soviet industry could not match Western capabilities. Western intelligence agencies had long suspected Soviet technology theft, but the Farewell dossier provided comprehensive evidence of its scale and importance. It led to significant tightening of export controls through the Coordinating Committee for Multilateral Export Controls, known as COCOM, which restricted technology transfers to communist countries. The restrictions were not perfectly enforced, and Soviet intelligence continued acquiring Western technology through complex smuggling networks. But the tighter controls increased costs and slowed the flow of equipment and materials that Soviet industry desperately needed. Ryzhkov watched these developments from his position at Research Institute Pulsar, continuing to manage programs that attempted to develop indigenous Soviet semiconductor technology while knowing that they would never achieve parity with Western industry. He mentored younger engineers, trying to instill in them the technical rigor and systematic approach that he had observed at Intel, but he could not overcome the structural limitations of the Soviet system that made excellence nearly impossible. The contamination problems that plagued Soviet cleanrooms were never adequately solved. Facilities that were supposed to be Class 10,000 often operated at Class 100,000 or worse because air filtration systems broke down and were not properly maintained, because workers brought contamination into the cleanrooms on improperly cleaned garments, because the buildings themselves leaked dust and particles from deteriorating infrastructure. Chip yields remained catastrophically low, typically 20–40% for complex integrated circuits when Western facilities achieved 70–80% yields for even more complex designs. The equipment problem was intractable. Soviet machine tool industry could not produce the precision manufacturing equipment that semiconductor fabrication required. Photolithography steppers built in Soviet facilities lacked the optical quality and mechanical precision of Western equivalents. Etching systems were crude and inconsistent. Deposition equipment could not achieve the uniformity and purity that modern chips demanded. Every piece of equipment was inferior to its Western counterpart, and the cumulative effect of using inferior equipment at every stage of the manufacturing process was that Soviet chips were inferior even when the designs were stolen directly from Western products. The materials problem was equally severe and equally unsolvable within the Soviet economic system. Western companies like Dow Corning and Monsanto supplied ultra-pure chemicals to semiconductor manufacturers, competing to provide better quality at lower prices. Soviet chemical facilities, operating as state monopolies with no competition, had no incentive to improve quality and lacked the investment capital to upgrade their purification processes. Silicon wafers arrived at chip fabrication facilities with impurity levels 10 to 100 times higher than Western specifications. Photoresist materials had inconsistent chemical compositions that made precise pattern transfer impossible. Process gases contained contaminants that introduced defects into the chips. By the mid-1980s, Soviet microelectronics leadership finally began to acknowledge publicly what engineers like Ryzhkov had been reporting for years. The technology gap was real. It was large and it was growing. Articles appeared in Soviet technical journals admitting that domestic chips were inferior to Western products, that manufacturing methods needed modernization, that the industry required fundamental reform. Under Mikhail Gorbachev's glasnost policies, these discussions became more frank, with engineers speaking openly about the systematic problems that prevented Soviet industry from competing with Western technology. But by then, it was too late. The economic problems were too severe, the technological gap too wide to close through incremental reform. The Soviet Union itself would collapse in 1991, and with it would go the centralized microelectronics industry that had never succeeded in matching Western capabilities despite decades of effort and massive investment. Ryzhkov retired from Research Institute Pulsar in 1989, 2 years before the Soviet collapse. In 1995, a Russian technology magazine interviewed him about his career, and the interviewer asked about his 1982 visit to Intel. The question had clearly been waiting for years. I knew Soviet microelectronics would never catch up the moment I walked into that clean room at Intel, Ryzhkov said quietly. Not because Soviet engineers were less capable, but because we were trapped in a system that made excellence impossible. The Americans had built an industry based on competition, quality, continuous improvement, and access to global supply chains. We had an industry based on central planning, guaranteed markets, production quotas that incentivized quantity over quality, and autarkic isolation that forced us to manufacture everything domestically, even when we lacked the capabilities. No amount of individual brilliance could overcome those systematic disadvantages. Did you report this to Soviet leadership? The interviewer asked. Of course, I wrote a comprehensive report. So did others in the delegation. We documented everything we saw, analyzed the implications, recommended responses. The reports went to the highest levels of government. And what happened? Ryzhkov gave a bitter smile. Nothing happened. The leadership could not admit that the American system worked better than Soviet planning. They could not acknowledge that competition drove innovation more effectively than state direction. So they filed our reports and continued doing what they had always done. We kept trying to build chips using methods that guaranteed we would fall further behind every year. And eventually the whole system collapsed under the weight of its own contradictions. The interview was published in a small circulation journal and mostly forgotten. But it captured something important about why Soviet microelectronics failed, despite having talented engineers, despite massive investment, despite acquiring Western technology through espionage. The failure was not technical in the narrow sense. It was systemic. The Soviet economic model could not generate the continuous innovation, quality improvement, and supply chain excellence that modern semiconductor manufacturing required. Ryzhkov's 1982 report, declassified decades later, stands as testimony to a failure that was documented thoroughly and ignored completely. The Intel visit had been intended as a technology exchange, an opportunity for Soviet engineers to learn about American manufacturing methods. In that narrow objective, it succeeded beyond what anyone probably expected. Ryzhkov and his colleagues saw exactly what they needed to see, understood the implications perfectly, and reported truthfully about what it meant for Soviet competitiveness. But Soviet leadership could not respond effectively to that information. They were trapped in an ideological framework that made learning impossible, that required maintaining comfortable fictions, even when those fictions guaranteed eventual failure. They could not acknowledge that their entire approach to industrial organization was inferior to Western capitalism, without undermining the basis of Communist Party rule. So they continued building inferior chips with obsolete equipment, using contaminated materials in poorly controlled environments, falling steadily further behind Western industry until the day the Soviet Union collapsed and the pretense could no longer be maintained. And in the archives, researchers found reports like Ryzhkov's, accurate assessments from competent engineers who had seen clearly how far behind Soviet technology had fallen, and who had been ignored because the truth they documented was too threatening to acknowledge. The clean room at Intel that had so impressed Ryzhkov in 1982 was itself obsolete by the standards of what Intel would build in later years. The 1.5 micrometer process that seemed impossibly advanced to Soviet engineers was primitive compared to the 0.1 micrometer and smaller processes that became standard in the 1990s and 2000s. The semiconductor industry continued its relentless advance, doubling transistor density approximately every 2 years according to Moore's law, pushing the boundaries of physics and engineering in pursuit of faster, smaller, cheaper chips. Soviet and later Russian microelectronics never caught up. The structural problems that Ryzhkov identified in his 1982 report persisted after the Soviet collapse, manifesting in different forms but with similar effects. Even today, Russia lacks an advanced semiconductor manufacturing capability comparable to Western, Asian, or even Chinese facilities. The country that sent the first satellite into space, that built nuclear weapons and intercontinental ballistic missiles, that competed with the United States across multiple dimensions of military and technological power, never mastered the art of manufacturing the tiny silicon chips that power modern civilization, and it all traced back to the moment when engineers like Ryzhkov walked into Western clean rooms, saw what modern semiconductor manufacturing looked like, understood immediately how far behind they were, and filed reports that were accurate, comprehensive, and ultimately useless because the system could not respond to the truth they contained.